Array traversing. The traversal operation involves accessing and processing an array element exactly once. It is also called visiting. In order to traverse the array, we set up a loop with index varying from the lower to the upper bound. In each loop cycle, an element of array is accessed and processed according to the requirement. Some examples of traversing an array are finding the largest element, finding the smallest element, computing average of all elements, and printing contents of array. We now consider the implementation of these operations. Implementation of array traversing. A class for traversal of arrays is shown. It includes 4 methods to process an array of real numbers. Maximum determines the largest element in the array. Minimum finds the smallest element in the array. Average computes the average of all elements included. Display prints the array elements. The detailed coding of all methods is given in the demonstration. Performance of array operations. We have already seen that the time efficiency of access operation is O1. Let us examine the running time for deletion, insertion, and traversal operations. As discussed, in order to remove an element from the array, all elements to the right of the element being considered are shifted 1 position to the left. Thus, if the first element is deleted, there will be altogether n-1 shifts for an array of size n. Since shifting is the only major operation in deletion, we can conclude that the running time of deletion is On-1 or On in the worst case. If the last element is to be deleted, no shifting would be involved. Thus, best case has running time O1. The insertion operation is similar to the deletion operation, except that elements are shifted in the opposite direction. Thus, in worst case, the running time of insertion operation is On. To perform a traversal operation, we normally set up an iterative loop. In each loop, an element is accessed only once. Thus, altogether n accesses are made. As such, the time efficiency of traversal is On. There are no best or average cases, since all the elements need to be visited at least once. Two-dimensional array. Sometimes it is useful to group the elements of an array into smaller groups of equal size. Thus, each subgroup can be viewed as a smaller array within an array. This arrangement is referred to as two-dimensional array. For example, test scores of a group of students may be organized by student number and for each student by semester number. A two-dimensional array can be pictured as consisting of rows and columns. Figure shows such a representation for student scores by semesters. Formally, a two-dimensional array is a collection of homogeneous elements which are arranged into rows and columns. In order to identify individual elements, we need 2 index sets, one for the rows and other for the columns. The indexes follow the array name and are enclosed in a pair of square brackets. For example, if marks is a two-dimensional array, marks JK refers to the element is in jth row and kth column. In C, C++, the rows and columns are counted from 0. Thus, mark 00 would refer to the element in the first row and the first column. As with one-dimensional array, a two-dimensional array must be declared before it is actually processed. The declaration should specify the maximum number of rows and columns besides the array type and name. For example, in C++, the array portrayed in figure might be declared as storage structure for two-dimensional arrays. The elements in a two-dimensional array are stored in contiguous memory locations. Within the allocated memory, the elements may be stored row by row or column by column. The first arrangement is called row major and the second column major storage scheme. Figure shows a row major and column arrangements of an array consisting of 2 rows and 3 columns. If we know the address of the first element, we can compute the storage addresses of all the elements. For a row by row arrangement, the address of an element AJK consisting of n rows and m columns is given by the formula. In this formula, base address is the storage address of the first element A00 and size is the number of bytes allocated to an array element. It is assumed that both the indexes have 0 lower bounds. For column by columns arrangement, address formula is. These formulas are used by the compiler to locate and access an element of a two-dimensional array. Thus, all elements have direct access. This is the prime reason for time efficiency of multidimensional arrays compared to other types of data structures. String arrays. Two-dimensional arrays are useful in storing and processing of strings. A string is a sequence of characters which are normally stored in a one-dimensional array. In C, C++, a string includes a null as terminating character as shown in the figure. Notice that the last character in the array is null character. Thus, a string of size n is stored in a one-dimensional array of characters of size n plus 1. In several applications, such as text processing, we need to store a group of related strings. These could, for example, word in a text block or names of employees. Two-dimensional arrays provide a convenient and simple mechanism to store a set of strings. Figure shows a two-dimensional array which contains the names. This representation has the advantage that, apart from having access to the strings, we can also access individual characters in each string. Since in two-dimensional array, all rows must be of the same size, we need to allocate same number of columns for all strings, irrespective of their size. Thus, unless the strings are of fixed size, some of storage space may be wasted. Operation on strings. We can perform several operations on strings that are stored in an array. Some common useful operations are inserting new strings into array, deleting an existing string, searching for a string, sorting in specified order, and listing strings. The algorithms for string operations are same as those for a one-dimensional array. However, their implementations differ. In C, C++, for example, strings cannot be assigned to variable. Instead, library functions are used for copying and comparing strings. For this purpose, the header file string.h needs to be included in the actual implementation. The interface class for string operations is shown in figure. It is designed to hold up to 20 strings, each with a maximum of 20 characters. The array is named X. It includes 3 common operations on strings. Add appends a string to the array. Del removes an existing string from the array. Insert adds a new string to array in a specified order. And disp prints the strings. Code skeleton for the basic class functions are given in the demonstration. Performance of two-dimensional array. A two-dimensional array allows direct access to any of the elements. Thus, accessing and assigning operations have a running time O1. For other operations such as inserting, deleting, and traversing, generally two nested loops are used. If the array consists of n rows and m columns, the loops would involve n into m cycle. Thus, the time efficiency for insert, delete, and traversal is O(n) into m. Matrix representation of arrays. A two-dimensional array of numbers is sometimes referred to as matrix. Matrices are frequently used in computer science and engineering disciplines. In graph theory, for example, matrices are used to represent links between nodes. Image processing application stores pixel values in rows and columns for different kinds of transformations. In mathematics, matrices are frequently used to solve a set of algebraic equations. Matrices are commonly used in quantum mechanics to compute energy spectra. In engineering applications, matrices are frequently employed for structural analysis. In mathematics, the subscript notation is used for the matrix element. Further, the elements of a matrix are enclosed in a pair of large brackets. Figure shows a pictorial representation of a matrix consisting of n rows and m columns. It is called n by m matrix. A matrix with the same number of rows and columns is called square matrix. The elements of a matrix with the same subscripts are referred to as diagonal elements. Thus, A11, A22 up to ANN are the diagonal elements of an n into n matrix. A matrix is called symmetric matrix if the corresponding elements below and above the diagonal elements are identical. Thus, in a symmetric matrix, Aij is equal to Aj for all j and I. Distance between several cities, for example, can be represented as a symmetric matrix. In some applications, matrices contain only a small number of non-zero values. Such matrices are known as sparse. A special form of a sparse matrix is called tridiagonal, in which all elements above the main diagonal are 0. The elements of a tridiagonal matrix can be stored in one-dimensional array. Figure shows an example and the correspondent array. Notice that the matrix with 16 elements is stored in an array of 10 elements. It can be shown that in general an n by n tridiagonal matrix can be stored into one-dimensional array of size n(n-1) by 2. In this way, a large economy of storage space can be achieved. Matrix operations. Common operations on matrices are addition and multiplication. The sum of pair of matrices is obtained by adding correspondent elements. Thus, if A and B are two matrices having same number of rows and columns, their sum C is given by for all values of indexes I and j. Matrix multiplication is somewhat more involved. The product of a pair of matrices is obtained by multiplying all elements in the correspondent column of first matrix with all elements in the corresponding row of the second matrix and adding together products of elements. If C is the product of matrix A and B, the elements of C are given, assuming that both A and B are n by n matrices. In mathematical notation, the expression can be simply written as where I and j vary from m to n. The symbol sigma represents sum over the index k, which varies from 1 to n. Three-dimensional array. A three-dimensional array is a collection of homogeneous ordered data elements which are accessed using three index sets. The indexes are enclosed in three pairs of brackets which are preceded by the array name. Each index set has its lower and upper bounds. In C++, the lower bound is 0. The three-dimensional array extends the notion of grouping of elements at three levels. For example, student scores might be grouped by student numbers, semesters, and subjects. The first index would refer to the student number, second to semester number, and third to subject number. Figure shows a pictorial representation of a three-dimensional array score. Notice that the array is split into 4 tables for the convenience of pictorial representation. Inside the computer, all of the elements are stored sequentially in contiguous storage location. The elements of a three-dimensional matrix are described in terms of rows, columns, and planes. The array M of test scores consists of 4 rows, 3 columns, and 4 planes, which refer to student number, subject, and semester. For example, M 0, 2, 3 represents the score of the first student in third subject in fourth semester. Advantages of array. Major advantages associated with the array data structure are: Number 1. It is possible to use a single variable for handling a large set of homogeneous data. Number 2. Arrays provide direct access to any of the data items. Thus, storage and retrieval of information are both fast and flexible. Number 3. It is easy to construct and use arrays. Almost all programming languages support creation and initialization of array with the help of simple declarative statements. Number 4. Arrays are indispensable in implementing iterative algorithms. It is easy to set up loops by taking advantages of array index sets. Number 5. Multidimensional arrays facilitate grouping of homogeneous data items into hierarchical structure. Limitations of array. Arrays have certain limitations as well. Their main disadvantages are: Number 1. Array size cannot be increased or decreased during runtime. Thus, arrays are not useful for applications which use large data set of unpredictable size. Number 2. Variable length strings cannot be efficiently stored into arrays because large amount of storage space will be wasted on account of padding space characters. Number 3. Insertion and deletion operations on arrays are not efficient. Every time some data item is added or removed, a large number of elements may need to be shifted. Number 4. Normally, arrays are allocated memory blocks out of the program space. For very large data sets, the program may run out of the storage space. Number 5. Some of the programming languages, such as C, C++, do not perform range check on array indexes. If an index has trespasses the upper or lower bound, incorrect data may be accessed or stored in wrong location. Some of the deficiencies of array are overcome in other data structures, which we will study in subsequent units.